Hey everyone, welcome back to Calculus 2. This will be lecture 7 of the course, and in this lecture we're going to talk about the natural logarithm. So I think we've touched on this previously, I think back in section 1.2 when we were discussing antiderivatives in general. I think we might have touched on some of this a little bit, or we might have touched around this idea. But we're going to explore it in more detail here. So let's jump into it. So let's call this section 1.7 the natural logarithmic function, and specifically integration. Okay. So as I say, previously we saw that the integral of 1 over x dx was equal to the natural log of the absolute value of x plus c. Okay, and I think further we also saw that the integral of 1 over u du was equal to the natural log of the absolute value of u plus c. Now, because du is equal to u prime dx, it's also true that the integral of u prime over u times dx is equal to the natural log of u plus c. Right? So this in particular, we're going to be messing around with in the coming examples. Okay? So I think most of this section will be lots and lots of examples. So let's jump right into a few. So kind of starting off simple, let's find the integral of 1 over 2x dx. Okay, so in this case, we can let u equal 2x. Okay, so then du is equal to 2 dx, right? So here's what we have. We have the integral of 1 over 2x dx is equal to 1/2 times the integral of 2 over 2x dx. Right? And then so we can do our substitutions here. We have the 2 dx is du and 2x is u. So it's 1/2 times the integral of 1 over u du. And here's where we see basically the previous result, right? So this would be 1/2 times the natural log of the absolute value of 2x plus the integration constant. Okay, so just a straightforward example. Let's do another one kind of like this. So in this case, we're going to find the integral of 1 over 4x minus 1 dx. Okay, similarly, let's let u equal 4x minus 1. Then du is 4 times dx. Okay, and so the integral of 1 over 4x minus 1 dx is equal to, right, same trick, right, multiply and divide by 4 simultaneously, and you get the full substitution here. 4 dx is du, and 4x minus 1 is u. And we have 1/4 times the natural log of the absolute value of u plus c, so 1/4 times the natural log of the absolute value of 4x minus 1. Okay, right, so that's the indefinite integral there. So very good. So the idea here is that I think what we'll find in this section is that these expressions that we've touched on previously have a lot of different applications, right? Especially when we combine this this integral here with the u substitution and the change of variables that we've done in the most recent sections. Okay. Here's another example. Let's find the area. Find the area of the region bounded by the function y equals x over x squared plus 1 between the x-axis, the y-axis, or sorry, the region bounded by this function, the x-axis, and the line x equals 3. So let's plot this. And so when you plot this, so this is like 0.1, 0.2, 0.3, 0.4, 0.5. So the plot kind of comes up to a high point here, and then it turns back down. Okay, maybe not quite that dramatically, but somewhere over here we've got 3, 2, 1. And so what we're interested in is the area here. So you notice, in the description, there's only one vertical endpoint, and that's because the function itself ducks below the x-axis before it intercepts the y-axis. Okay, so this is a definite integral, and it would look like this from 0 up to 3. Okay, on the x-axis of x over x squared plus 1 dx. Now, so here we'll want to use a u substitution, so we'll let u equal x squared plus 1, then du is equal to 2x dx. Okay, and we can use the same trick that we've used in the past few examples. And it will basically divide and multiply by 2. Right, like so. And in doing that, then we get 1/2, and the x squared plus 1, that's u, and the 2x dx, that's du. So this is a straightforward 1 over u du. And we get 1/2 times the natural log of the absolute value of u, which is x squared plus 1, plus c. Okay. And so, well, actually not plus c, this is a definite integral, so we're integrating from, I should put that on here, from 0 up to 3. Right, so we get 1/2, and then it's going to be the natural log of the absolute value of 3 squared, which is 9, plus 1, minus the natural log of 0 plus 1. And so when we get that, let's see, all together we have 1/2. And then it's the natural log of 10 minus the natural log of 1. And so this is 0, and all told we have the natural log of 10 over 2, which is, approximately 1.15-ish. Okay, so that's the area underneath the curve here, bounded by the region, or bounded by the line x equals 3 and the x-axis. Okay, very good. Another example. So let's calculate the integral 3x squared plus 1 over x cubed plus x. Okay, so this guy here. So it's very similar to the previous examples. We'll let u equal x cubed plus x, right? Then du must be equal to 3x squared plus 1. Okay, that whole thing times dx. Now, magically, this is a little bit of a contrived integral, but yeah, you can see that numerator is exactly as you'd want it. And so this is just the integral of du over u. And so it's the natural log of the absolute value of u plus c. And so it's the natural log of x cubed plus x plus c. All right. So far, so good. Pretty straightforward examples so far. Okay, pretty straightforward. Let's mix things up a little bit with another example here. How about we pull in some trig functions here? Let's integrate secant squared of x divided by tangent of x. Okay, so here let's try, you may want to try some things, but one of the things you would certainly try is letting u equal to the tangent. Okay, then du is equal to secant squared x dx. Okay, and this one comes, again, if you can recall that the derivative of tangent is secant squared, this one is relatively straightforward. So this is equal to, again, 1 over u du, so the natural log of the absolute value of u plus c, which is the natural log of the absolute value of the tangent function. Okay. All right. Very good. How about, let's try this one. Again, repetition is kind of the king here. Let's look at this integral. This will be x plus 1 over x squared plus 2x. All right. And let's let u equal x squared plus 2x. Then du is 2x plus 2. All right. Which is equal to, oh, sorry, du dx here, right? So make sure we do that. And so that actually means that du is equal to 2 times x plus 1 dx, right? So it looks a bit like that. All right. And so then we can come in here and we can do our multiply divide trick. So that's going to be equal to 1/2 2 times x plus 1 over x squared plus 2x, like so. Okay, and so then you've got the denominator here is u, and the numerator with dx is your 2 times x plus 1 dx. So this again is just 1/2 times the integral of 1 over u du, which is 1/2 the natural log of the absolute value of u. And plugging back in the x, we get that guy right there. So again, another example where the integral doesn't look like it's going to quite fit, but we can mess around with it and get what we need. Okay. How about another example? So through all of these examples, hopefully you're kind of gleaning how useful and versatile this natural log rule is. So let's take a look at it. This one. This will be the integral of 1 over 3x plus 2 dx. And so this one is just the same as the previous ones, right? Let u equal 3x plus 2. Du is equal to 3 dx. So then this guy here is 1/3 times the integral of 3 over 3x plus 2 dx, which is 1/3 times the integral of 1 over u du. And so it's 1/3 times the natural log of u, which is 1/3 times the natural log of 3x plus 2. Okay. All right. Good. How about let's toss in something kind of left fieldish here. What about this one? This one's a little more left field. This is one we haven't seen. This is going going to involve a technique that we haven't seen. The integral of x squared plus x plus 1 divided by x squared plus 1. Okay, so now in this case, a straightforward u substitution like what we've been doing is not going to work. So we need to really like rewrite this integrand. And one of the things you'll notice here is that, and one of the things that kind of might be prompted to come to your mind here, is polynomial division, right? So actually, if you recall back in the days of pre-calculus and maybe college algebra, you would have come across a section on polynomial long division. So in cases like this where you've got a numerator and denominator, they're both polynomials, and the numerator's degree is greater than or equal to the denominator's degree, polynomial division can be a highly useful tool for like rewriting the integrand and introducing opportunities for making the integrand something that we can integrate or something we can use our existing integration rules for. So this is one of those cases where you can take your x squared plus x plus 1 and you can divide it by x squared plus 1. Okay, and so what we would say is x squared plus 1 goes into this whole thing one time, right? And then so multiplying that'd be 1 times x squared is x squared, and then you get a plus 0x, and then 1 times 1 is 1. Right, so then this whole thing can be subtracted. And so x squared minus x squared is 0, and then x minus 0x is x, and then 1 minus 1 is 0. So the remainder here is x. Okay, and so what that means is, that x squared plus x plus 1 over x squared plus 1, right, so the original integrand, is equal to 1, right, 1 plus the remainder x divided by x squared plus 1. Okay, so basically I can substitute this into the original integral. So let's do that and see if that helps us. X squared plus x plus 1 over x squared plus 1 dx. That's equal to this. So the integral of 1 plus x over x squared plus 1. Right, and so you can see pretty quickly that this is going to be great because we can break the integral up into two pieces. This is the integral of a constant, no problem. And then this piece over here is going to work with a u substitution. So this, namely, if we let u equal x squared plus 1, then du is 2x dx, and we can apply the same trick that we've been using. Okay, so let's break this up. So this would be the integral of dx plus the integral of x over x squared plus 1 dx. So we've got those two pieces. And then this part's clean and straightforward. This part, if we're going to let u equal x squared plus 1, then du is going to be 2x. So what we'll want to do is write this as 1/2 times the integral of 2x over x squared plus 1 dx. Then we can come in here and we can say let u equal x squared plus 1, then du is equal to 2x dx, right? And that'll take care of this piece here. Okay. And so we've got integral of dx is just x plus 1/2, and then this piece would be the natural log of, just kind of doing it in one quick step, it would be the natural log of u, which is x squared plus 1. Okay, and then the whole thing plus c. Okay. Yep. Let's clean it up just a little bit more here. So it'll be x plus, well, I guess not too much more, 1/2 times the natural log of x squared plus 1, just like so. I just skipped a step in there, but yeah, I think it's going to be the exact same trick that we've used like 5 times already. in this lecture. So very good. How about this example? Let's take a look at something like this. X plus 1 quantity squared. Right, so 2x divided by x plus 1 quantity squared dx. Okay, so something like this. Let's explore the u substitution angle. Let's let u equal x plus 1, then du is equal to just dx. Okay. And then we can use this thing here, right, to say that u equals x plus 1 implies x equals u minus 1. Okay, because so the x plus 1 takes care of the denominator, be u squared. The dx, it becomes du, but we're still left with this 2x, and so that's why we need this third piece here. Okay, so really we're going to have 1, 2, 3 substitutions to make here. So let's plug all that in and see what it looks like. Okay, so the 2x becomes 2 times u minus 1. Okay, x plus 1 quantity squared becomes just u squared. And then the dx is du. Okay, and so kind of similar to before, we can break this integral up into 2 pieces. Okay, and so we'll want to do that. So you'll want to take kind of this portion here as the first integral. So that'll be 2u over u squared du. And then the second piece would be plus the integral of negative 2 over u squared du. Okay, make sure you kind of drag the negative along with it, or you can, I guess, equivalently, you could put a minus between the integrals. And so let's clean this up just a little bit more before we do the actual work. Here you get a cancellation. So it'll be 2 times the integral of 1 over u du. That's nice. That's very familiar. And then here it'll be plus negative 2 times the integral of u to the negative 2. Right? So here we're going to use the power rule. And so what do we get? Well, we get 2 times the natural log, the absolute value of u over here, minus 2 times, now what happens here? What happens in the case of u minus 2? Well, here's where we use the power rule. So this would become u to the negative 2 plus 1 over negative 2 plus 1, right, like so, and then the whole thing plus c. So you might be able to just do that in your head. But just to make it clear exactly what is being applied here, I just sort of wrote it out. So it'll be twice the natural log of u, and then this is going to be a negative 2, and this will be a negative 1 in the bottom, so altogether this will be plus 2. And then it'll be u to the negative 1 power, correct? Yep. And so coming back through, and recall that u is equal to x plus 1. We can plug everything back in. And we get twice the natural log of the absolute value of x plus 1 plus, and now I'm going to make it 2 over x plus 1. And there we have it. Right, so that one's got some of the old tricks, right? Some of the new tricks. Okay. All right, so let's see. So we've covered a lot of ground here. We've done a lot of examples involving this. Let's kind of consolidate some of what's gone on here. So what we're interested here in is just guidelines for integration. Okay. Okay. So how to approach integration in general. Right, and we're going to update these guidelines as we go forward, right? But this is like a sort of State of the Union kind of thing here. Where are we at right now? Okay, so guidelines for integration. Learn a basic list of integration formulas. right? So we've seen a bunch of those, right? So we've seen a bunch of those. We've got, like, for example, the ones we've been, looking at, the trig, like, well, let's start with this one. Integral of 1 over u is natural log of u, right? That's one that we've seen. Integral of the trig functions, right? So like the integral of, for example, sine of x is negative cos x. Okay. Etc., right? So we've seen a whole bunch of these. We've seen a bunch of these already, and there's more to come. So the key here is to just, you don't necessarily have to memorize these things. What's more important is having done enough examples that you can look at an integral and you can take a guess at where to go next, right? You can look at an integral and say, oh, there's something about that that's telling me that maybe, something like this is going to be appropriate, or maybe it's just a basic u substitution, or hey, there's trig functions in here, I can use those, or it's an even odd function, it's a definite integral, so I can use theorems that we've seen in the past for that, right, etc., etc. Right, so it's not that you have to memorize anything, it's more that you need to have, my recommendation would be to do enough examples, practice enough problems, that when you see a new problem, it's not totally, it's very likely that you've seen something similar. So that's first step. And so kind of like step 2 is to, obviously find an integration formula, from what you know, or, what you can recall. Find an integration formula that resembles all or part of the integrand, and by trial and error kind of find a choice of u that will make the integral conform to the formula. Right, so find a formula that resembles all or part of the integral of the integrand. And then by using, trial and error, find a choice of u. Okay, that makes the integral makes the integral conform to your formulas. Right, so that's kind of the basic. Right, and so if it may be the case actually that you just can't find a u substitution that does the trick, right? So it's very likely that you'll look at an integral and say, oh, geez, none of these u substitutions lead me to give me the ability to do like a change of variables and to tackle this integral. So if you can't find a u that will work, you need to try to alter the integrand in some way. So if you can't find a u sub that will work, you'll have to try to change the integral, the integrand in some way, right? Right, and so similar to the example that we did with the long division, right? There was nothing, it was not obvious how we would ever use a u substitution to solve that, but the fact that it was a polynomial divided by a polynomial and that you could do polynomial division on it gave us an opportunity to make it, to change the integrand and ultimately ultimately integrate it. Right, so some examples here would be like trig identities, big ones there. Right, like, if you went through pre-calculus or even had a full-blown trig class, there's gajillions and gajillions of trig identities. And so anytime you're dealing with an integral that has trigonometric functions in it, trig identities can be a resource. Right, you can just use algebra also. Right, so sort of like polynomial division. There's another one called partial fractions, which we'll talk about later. But just anything you can do to alter the integrand is something that you want to try, right? If you just need to change it, you need to figure out a way to re-express the integrand so that it makes sense from the standpoint of integration. And then if all else fails, you could use software. All right, so we haven't really done much of that, but nowadays your calculators and your Wolfram Alpha, these things are exceptional tools for understanding, both learning calculus and actually like just doing the work of calculus, like calculating integrals. Okay, so this is like a nice, just again, a guideline for integration, state of the union kind of thing, right? So we know we have a super powerful technique called change of variables, U substitutions, and so that should kind of be your default go-to, right? So find a formula that resembles the integrand, try to make a U substitution work, right? That's kind of your start, usually a good starting point, right? If it's not something really obvious like integral of sine or something. If that doesn't work, then you want to start thinking about how can I change the integrand, how can I re-express things, right? And so all of your experience with algebra and trigonometry will come into play here. Okay, and then if all else fails, you could use software or like a table, integration by tables. We'll talk about that later. We haven't gotten to that yet, actually. So, excellent. Let's see. Let's take a look at some more examples. Let's start. Let's flip the page here. So we're going to be jumping into differential equations here in a few sections. So let's take a look at an example of a differential equation. So let's solve the differential equation. And we'll say it's dy dx equals 1 over x times the natural log of x. So this is a differential equation. Now remember, a differential equation, the solution to a differential equation is basically an equation that involves a variable y that it doesn't contain any derivatives, right? So you can kind of think of it like that at the onset, anyways. And so something like this, we can start chugging away on this. We can say this is, well, first thing we can do is separate the dy and the dx here. So you get dy equals 1 over x ln x times dx. Okay. Now anytime you see dy all by itself over here, you can integrate and that becomes y. So what we'll want to do next is integrate both sides of the equation. And so you get y equals the integral of 1 over x ln x dx, right? So then if we let u equal ln x, right? Okay, so let u equal this piece of it, then we know that du is equal to 1 over x, right? Remember that derivative, right? And so we actually have the u is the 1 over ln x, so it's the u is ln x, and then the 1 over x dx is the du, right? So y equals the integral of 1 over u du, and we can quickly calculate that as the natural log of the absolute value of u plus c. And so that means y is equal to the natural log of the absolute value of the natural log of x. Okay, not the prettiest equation in the world, but it works. Okay, so we'll get into differential equations a lot more in the coming sections. And then after Calculus 2, there's a course called Differential Equations, Ordinary Differential Equations, where these kinds of methods will be explored in a lot more detail, right? A lot more detail. And then we'll get into, when we take that course, we'll get into much more sophisticated types of differential equations. Let's see. Here's another example. Let's integrate the tangent of x. Okay, so this is one that we've talked about what the integral. I think we've talked about. Well, maybe we haven't actually. No, we haven't. We've only talked about sine and cosine so far. Okay, so this is going to make use of this natural logarithmic function. So the integral of the tangent. So the integral of the tangent is equal to the integral of sine over cosine. Right? Tangent is just sine over cosine. Okay. Now, if we come off to the side here, and let's say that u is equal to the cosine of x, then du is equal to negative sine x dx, right? Okay, and so we've almost got that in this expression. What we don't have is the negative, right? And so what we can do is we can make this equal to negative integral of negative sine x over cos x dx, right? So we've multiplied and divided by, we can kind of think of it as multiplying and dividing by -1, or multiplying by -1, which however you want to think about it. Okay, and then so once we have that, though, then we have all of the substitutions needed. And so this would be negative integral of 1 over u times du. And so you'll see we get negative natural log the absolute value of u plus c. And so then u is cosine, right? And so this guy becomes the negative natural log of the absolute value of cosine of x plus c. Okay, so that's nice. We hadn't talked about how to integrate tangent, and now we can see that it's the negative natural log of the absolute value of cosine. Okay, let's do another trig example. This time let's talk about the secant. So the integral of secant x dx. Okay. So this is one where we're gonna have to be kind of tricky here. So I'm going to start by changing this the integrand here, and what I'm going to do is I'm going to multiply the top and the bottom by secant x plus tangent x. So this is an example of a tricky algebraic move, right? And you'll see in a second why we're doing this. But so if I do that, I get secant x over 1. I'm just going to make it explicit what I'm doing here. And then you're going to multiply and divide by secant x plus tangent x, like so. And then let's go ahead and simplify that a little bit, and I get secant squared x plus secant x tangent x on the top, and then secant x plus tangent x on the bottom. Okay, now why in the world did I do this? Well, because it's going to work. So let's let u equal secant x plus tangent x. Okay, basically the denominator here. And then du, what is du? Well, the derivative of secant is secant tangent, and the derivative of tangent is secant squared. And so we get exactly this numerator. So it's going to be, du is going to be equal to secant x tangent x plus the derivative of tangent is secant squared x. Okay. And so that's the numerator. Okay, so perfect. We can then say that this is equal to the integral of 1 over u du. And so, of course, that's going to be the natural log of the absolute value of u plus c, which in our case is the natural log of the absolute value of secant plus tangent. Okay. All right. So that's the integral of secant. Now, it turns out that basically all of the remaining trig functions will make use of this natural logarithmic function. Let's go ahead and just summarize those results, and I'll kind of let you guys can do that on your own. But the integrals of the 6 basic trig functions Right, so the first one we've seen a long time ago, that's the sine of u du is equal to the negative cosine of u du, or plus c, sorry. Okay, that one we've seen. Similarly, the cosine of u du is equal to the sine of u plus c. Okay, now we just talked about the tangent, so the integral of tan u du. Okay, turns out that's equal to the negative natural log of the absolute value of cosine of u. Okay. And what about the cotangent? Well, it's going to resemble this one here. It's the natural log of the sine of u. All right. And the secant we just did. It's going to be the natural log of the secant of u plus the tangent of u. All right. And then finally, the cosecant. Right, this guy is equal to the negative natural log of cosecant plus cotangent. Right, and so you can go through and, so we did this one and we did this one. These other two can be done in almost identical fashion, right? So the cotangent, you start by converting, cotangent into cosine over sine, and then the u substitution follows directly, and you end up with this. And then the cosecant, you're going to want to do the same trick as what we did up here, multiplying by secant plus tangent, except in the case of cosecant, you have to multiply and divide by something different, but I bet you can figure it out. And so that's the setup. Okay, so these are very useful. These can be very useful. We will use these all the time going forward. Let's do an example with these trig functions. Let's evaluate a definite integral. So let's evaluate the integral from 0 up to pi over 4 of 1 plus tangent squared x, square root of that. Okay. So here's an example where a trig identity is useful. You may recall the Pythagorean identity. You certainly recall sine squared plus cosine squared is 1. But there's also a trig identity for tangent and secant, and that basically says that 1 plus tan squared theta is equal to secant squared theta. Okay, so this is the other Pythagorean identity. Okay, so it's the other Pythagorean identity. And so we can use that here. This 1 plus tangent squared is what we have inside the radical here. We can replace it with secant squared. Okay, so 0 up to pi over 4, 1 plus tan squared x dx. Well, that's just 0 to pi over 4 the square root of secant squared x. And this is nice because the square root of secant squared is just secant. And secant, the integral of secant is, well, we just talked about it, right? It is equal to the natural log of the absolute value of secant x plus tangent x. Okay, we'd have to evaluate that from 0 to pi over 4. And so we can do that. The natural log of the absolute value of secant of pi over 4 plus tangent of pi over 4 minus the natural log of the absolute value of secant of 0 plus tangent of 0. And what do we get here? Well, consulting your unit circle, your trig cheat sheet from back in the day, you will see that this secant pi over 4 is the square root of 2. Tangent of pi over 4 is 1. And secant of 0 is 1. And tangent of 0 is 0. Okay, and so let's see, we would get the natural log of basically 1 plus the square root of 2 minus the natural log of 1. And I'll let you guys plug that in for the approximation, right? There's some, whatever the decimal number happens to be, you can plug that in and check it. Okay, but these are just numbers at this stage, right? Let's pull up kind of something from the more recent section. What about let's try to find the average value. Find the average value of tan x on the interval 0 to pi over 4. Okay, so let's think about what this looks like. It doesn't really matter too much what it looks like, I guess, but we'll have 0, and then we'll say pi over 4 is out here. Now, we just saw that tangent of pi over 4 is equal to 1. Okay, so we'll say it's like up here is 1. Okay, and so we know that the tangent kind of increases, and it does one of these things here, right? And so it's kind of going to be going like this, right? We know there's an asymptote out here at pi over 2, right? So it's increasing, and so we're just interested in the average value of this function over this region. All right, and it's not a constant function, so it's not obvious. It's not going to necessarily be the midpoint here. It's not going to be like 1/2 or something. But let's go ahead and calculate this. How do we do this? Do you guys recall? This is going to be a few lectures back. We saw that the average could be calculated as 1 over b minus a times the integral from a to b of f of x dx. Right, that's basically the approach to take. And so our average is going to be equal to 1 over b is pi over 4, and a is 0, so this would be basically 4 over pi times the integral from 0 up to pi over 4 of the tangent of x dx. Okay, and so we can calculate this very quickly, right? Because we just went through it, and so we know that the integral of tangent is negative natural log of the absolute value of cosine of x, and that's going to be from 0 up to pi over 4. Okay, and so that means we have 4 over pi times, oops, I'm going to do the next line here, so that'll be 4 4 over pi times, now it'll be the negative natural log of cosine of pi over 4. Well, cosine of pi over 4 is square root of 2 over 2. Okay, so this would be negative natural log of the square root of 2 over 2. And then it's going to be minus the negative natural log of cosine of 0, which is 1. Okay, the natural log of 1 is 0, right? And so this whole piece is irrelevant, and the answer is going to be this guy here. So it's 4, we'll put negative 4 over pi times the natural log of square root of 2 over 2. Okay, now when you plug all of this into a calculator, what you'll see is that this is going to be approximately 0.441. Okay, and so it, if this is 1/2, then the average is like right about there. Okay. Excellent. Okay, all right. So that is everything from this section. And what we'll do next time is we'll jump into, we'll get into, so kind of continuing on with this theme of the trig functions, we'll get into the inverse trig functions next time and talk about arcsine, arctangent, all of those functions and where they fit into the integration scheme. So talk to you then.